Hello everyone, welcome to IIT-JAM in Chemistry tutorial number 9, and here we are in lecture number 5 of the chapter Atomic and Molecular Structure. In today's lecture we are going to discuss the Heisenberg's uncertainty principle and the Schrödinger Wave Equation. But before starting these subtopics, we have to carry forward one more question from the previous lectures. This question came in IIT-JAM in 2022. And the question is, the effective nuclear charge of helium atom is 1.7. The first ionization energy of helium atom is what? That means you have to calculate the first ionization energy of helium in electron volt. Now we know the energy relationship as a variable of Z and N. As a function of Z and N is energy is directly proportional to Z square by N square. Therefore, we can write, if this n square is taken to the left hand side, then En square by Z square becomes a constant, because if you remove this proportionality relationship, then it becomes an equation with a proportionality constant here. So this is some constant. So En square by Z square is a constant. That means E1 N1 square by Z1 square equals to E2 N2 square by Z2 square. Now for a hydrogen atom, this energy, we know that this is minus 13.6 electron volt, and this N1 means for the first orbit this is 1, so this is 1 square, and for hydrogen the nuclear charge is 1, so it is 1 square again, so minus 13.6 into 1 square by 1 square. Now for helium we have to find the value of E2, that means the energy of the electron in helium atom. So this value is unknown, but N2 is known. For helium also we have to take into consideration the electron of the first orbit. That is why it is also 1 square in the right hand side. And given that the effective nuclear charge, that means Z2, that means the effective nuclear charge of the helium atom is 1.7. Okay, so we have to put here 1.7 whole squared. And by solving this relationship, we can get the value of E2, which is minus 39.3 electron volt. If the energy of the electron is minus 39.6 electron volt, then the energy required to remove that electron is plus 39.3 electron volt. So the correct answer is 39.3, and here option C is the correct answer. Now move on to the Heisenberg's uncertainty principle. Now in the classical mechanics, if you want to see an object, you have to allow some light to fall on it, and then you can easily measure its position, and by its movement you can measure its by hitting the particle you can easily measure its momentum. You can easily take the mass of the particle, you can easily measure the velocity of the particle, and this way you can measure the momentum of the particle. But if the particle is a tiny particle, you cannot see it by a naked eye or by some microscope, then it is very difficult to determine the position of the particle and as well as its momentum, because in order to do that you have to hit that particle with light again. But light is photon, that is also a particle, that one has also particle behavior. Now when this particle of which is photon, which hits an electron, say a tiny particle, for example electron, then the electron changes its position due to collision with the photon. Not only that, there is a momentum transfer between the electron and the photon, and that is why there becomes a huge uncertainty in measuring in its position as well as in its momentum. So let's see. To see a tiny particle at rest, we have to hit the particle with photon. If light has wavelength lambda, then its position within a distance shorter than lambda cannot be determined due to diffraction. That means if lambda is the wavelength of that photon, then there becomes an uncertainty in the position of that tiny particle within the range of lambda. So lambda is the order of uncertainty in the measurement of position. A photon of wavelength lambda has momentum definitely h by lambda. This is according to the Broglie equation. When a photon collides with a tiny particle, it transfers this much momentum to the particle. and the uncertainty in its momentum is also h by lambda. So what does it mean? The photon has wavelength lambda, that means it has momentum h by lambda according to de Broglie's equation. Now if this photon hits that tiny particle, then this much amount of momentum, there is a possibility of this much amount of momentum to get transferred into that particle. So the momentum of the particle, tiny particle, can be measured, but there should be some uncertainty in the range of its momentum up to this value h by lambda. So the product of uncertainties in position and momentum is what? The uncertainty in position is lambda, while the uncertainty in momentum is h by lambda. So the product should be lambda into h by lambda, and the result is h. And if there is a more accurate treatment, then this value becomes a little bit less, and this value is h by 4 pi. Okay, so according to more accurate treatment of Heisenberg, this principle states, that means what is the Heisenberg's uncertainty principle finally? So this is in green color. If the momentum is known to lie within a range of delta px, so this is the momentum, uncertainty in momentum along, say, x-axis. So along the x-axis, the uncertainty in momentum is delta px, and along that same x-axis, if there is an uncertainty in its position up to an extent of delta x, then its product delta x and delta px is here, delta px into delta x is greater than equal to h by 4 pi. That means this is the minimum amount of uncertainty. It may be greater than that. So this is equation number 10, and this is the mathematical form of the Heisenberg's uncertainty principle. Now let's move on to the Schrödinger wave equation, but before that we have to discuss the wave equation of a de Broglie particle. Let us consider a particle which is moving along a circular path like this. Look at the movement of the cursor here. So it is producing some angle theta. So when here the particle is here, then the angle theta is 0, and its projection on the y-axis is here. Now if some angle in the positive direction is produced, like say here, then its projection becomes this one, and this value is the changing amplitude of this wave, because the projection moves along this y-axis according to the simple harmonic motion. So this is nothing but a simple harmonic oscillator, the projection or the shadow of this particle here on the y-axis, and this value of y can be related to this value of theta, because this theta is also here, this theta, and this is the right angle triangle which has this angle theta, and this is the hypotenuse. Then y by this hypotenuse is sine theta. That means y equals to sine theta. Now according to the graphical plot, this is the graphical plot which can be obtained by plotting y as a function of theta. Now if any particle which is a de Broglie particle, which has both wave and particle nature, then its movement can be compared with this sinusoidal path. In one cycle it completes 2 pi angle. So its phase 2 pi phase is completed in one cycle. So the movement of the particle can be compared with this path, which is a sinusoidal path. So the equation is what? Now the equation is y equals to sine theta. Now let's calculate the value of y. Y is the changing amplitude, and its maximum value is a, which is in turn the radius of this circular path. Therefore the changing amplitude y of the Broglie particle moving sinusoidally along x-axis, here it is in the positive direction, that is why in the plus x-axis, so the expression should be y equals to a sine theta. Now here we haven't written it theta. Why? First of all, why it is a sine theta? Let us discuss this. This angle is theta, so in turn this angle is also theta. Therefore this y divided by the radius, that is the maximum amplitude a, which is the radius, this is sine theta. Therefore y equals to a sine theta. A is the radius, and in turn it is the maximum amplitude from here to here. This is also the radius, so it's y equal to a sine theta. There is no doubt about that. Now y theta is twice pi by lambda into x. Now look at the movement of the particle, sinusoidal path, by following a sinusoidal path. Here, when the angle theta is produced, then this theta is produced in t time. Then if this theta is divided by t time, then its angular velocity, that means theta by t, is obtained, which is nothing but omega. Therefore theta can also be written as omega into t. Now if the angular velocity is omega and one complete cycle produces twice pi angle, then in 1 second it produces omega by twice pi number of cycles. So this is omega by twice pi equals to the number of cycles per second. That means this is the frequency. So this is nu per second. That means nu hertz. This is the frequency. That means the number of cycles per second. Therefore here in place of omega we can write this twice pi can be taken to the right hand side and it goes to the numerator. As a result we get twice pi nu. So instead of omega, here we have written twice pi nu, and then this multiplied by t. Now we know that the velocity c is actually the product of frequency and wavelength lambda. From this to this distance of these 2 points from here to here, this is lambda. So if lambda is multiplied with frequency nu, then the velocity c is obtained. Therefore nu is actually c by lambda. That is why here in place of nu we have written c by lambda. Now velocity when multiplied by time, then displacement x is obtained. So the movement along this plus x axis is written, if it is written as x, then in place of c into t we can write x. So as a result this is x by lambda. That means twice pi by lambda into x. That is why theta can also be written as twice pi by lambda into x. So this is the actually expression of changing amplitude y. Okay, and this is nothing but psi in our quantum mechanics, and this is the wave function. So what is the physical significance of psi? The physical significance of psi is the wave function that is actually describing a de Broglie particle, and psi is nothing but the changing amplitude of the movement of the particle, and its maximum value, this is a. Now in our terminology we can replace this y as psi and this small letter a by capital A, and finally it takes the form psi equals to capital A sine twice pi by lambda into x. Now move on to the Schrödinger wave equation, but here first of all the time independent, where there is no t, this Schrödinger wave equation we have to deduce. So the amplitude of the Broglie wave associated with a moving particle is what? What we have obtained? We have obtained psi equals to a sine twice pi by lambda into x. Now we have to differentiate both sides with respect to x. Then the left hand side becomes d psi by dx, and ddx of sine x equal to nothing but cos x. Okay, so that's why this is again cos of this angle, that means twice pi by lambda into x. Now this part is also differentiated with respect to x, and the value should be twice pi by lambda. So this is in the left hand side d psi dx. In the right hand side we get a cos twice pi by lambda into x into twice pi by lambda. Now double differentiating both sides, that means double differentiating psi, that means differentiating both sides of this equation, we get what? With respect to x we get what? Now this is d2 psi, and in the denominator dx squared. So this is d2 psi dx squared, and in the right hand side we know the differentiation of cos theta is minus sine theta. So this is minus sine the same angle twice pi by lambda into x. Now this twice pi by lambda into x again differentiated, so it would again produce the value twice pi by lambda, and here one more twice pi by lambda was existing previously. So this value is twice a into sine twice pi by lambda into x. So this is a into sine twice pi by lambda into x. So this value is nothing but psi. So in place of that we can write psi. So minus psi, then 2 into 2 4, pi into pi, pi square, lambda to lambda, lambda square. So we have written minus psi into 4 pi square divided by lambda square. This way we get equation number 12. And we have this equation number 12 rewritten here. Del to d2 psi by dx square equals to minus 4 pi square by lambda square into psi. That means we have just interchanged the position. That means rearrange this equation. Okay. Now let us discuss another thing, which is the kinetic energy of a moving particle. The particle has mass m and velocity v. Okay. Kinetic energy here, it is denoted as capital letter T. And we know that the expression of kinetic energy is half mv squared. So T equals to half mv squared. So half mv squared can also be written as mv whole square divided by twice m. Then mv we know is nothing but momentum. So it is momentum p. If p is written as momentum, then it is p square by twice m. So it is 1 by twice m into p square. Now according to the Broglie wave equation, it is momentum equal to h by lambda. So in place of p, we have written here h by lambda. So it is h by lambda whole square into 1 by twice m. As a whole, it is h square by twice m into lambda square. This is a printing mistake. Let me correct it. Yes, I have made the correction by pausing the recording here. So it was actually it was coming as L in English letter, but in Greek letter L becomes lambda. So we have made the correction here. So this is nothing but as a whole h square by twice pi into lambda square. Now if E is the total energy means potential energy plus kinetic energy, and if potential energy is denoted as V, then T can be written as E minus V, as here kinetic energy equals to total energy minus potential energy. Now T has the expression, overall expression, h square by twice m lambda square. So here we have rewritten this h square by twice m lambda square, and if this is rearranged, then we can get the expression of 1 by lambda square, as 1 by lambda square is equal to twice m by h square into E minus V. Okay. Now putting this value of 1 by lambda square in equation number 12. We already had equation number 12, a double differentiation form of psi, which is d2 psi dx square, and in place of 1 by lambda square we have written here this overall right hand side of this equation. That means twice m by h square into E minus V, and as a result we get here minus 8 pi square m by h square into E minus V into psi. So this is what happens when a particle moves along x-axis. So this is the one-dimensional form of the Schrödinger wave equation, time independent. So this equation, when rearranged, all the parameters taken to the left hand side, then it takes the form of equation 13, and equation 13 is the one-dimensional form of the Schrödinger wave equation. So let's block this. Now, following the one-dimensional Schrödinger wave equation, we can also write the three-dimensional Schrödinger wave equation, time independent. And just along with del 2 del x square, we can add here del 2 del y square and del 2 del z square, this operator, by operating psi. So it becomes finally del 2 psi by del x square plus del 2 psi del y square plus del 2 psi del z square plus 8 pi square m by h square into E minus V into psi equals to 0. So equation 14 is the 3D form of the Schrödinger wave equation, time independent. And if this operator is written together as del 2 del x square plus del 2 del y square plus del 2 del z square, then this is a very important operator which is known as the Laplacian, and it is denoted as this sign, inverted horizontally inverted delta square. So this is the symbol of a Laplacian operator. So this can also be written as this Laplacian psi plus 8 pi square m by h square into e minus p psi equals to 0. So this is equation number 15. Now this is, I haven't given any number here. Equation 14, actually this is another form of equation 14, and this is the Laplacian operator. So both equation 13 and 14 here are in the Cartesian form, not in the polar form. Polar form is bit different. Now move on to the questions. So for an electron whose x positional uncertainty is 1 into 10 to the power 10 meter, then the uncertainty in the x component of the velocity in meter per second will be of the order of, these are the options, and given mass of the electron 9 into 10 to the minus 31 kilogram, and Heisenberg's, this is Planck's constant is 6.6 into 10 to the minus 34 joules second, and this question came in IIT-JAM 2005. So here the uncertainty along the x-axis is 1 into 10 to the power 10 meter, and according to the Heisenberg's principle, uncertainty principle, we know that delta px into delta x is greater than or equal to h by 4 pi. Therefore here delta px can be analyzed into two components, which is m into delta p. That means m is the mass of the particle and delta p is the uncertainty in velocity. And here this is also, by rearranging, we can write this delta x, if taken to the right hand side, then delta px is greater than or equal to h by delta x into 4 pi. So this delta px is actually greater than or equal to 1 by delta x into h by 4 pi. So this is analyzed m into m into delta p. Okay, so this delta p, if we want to measure this delta p value, then we have to take this m into the right hand side here also. So finally we get this form of delta p, that is the uncertainty in velocity, which is h divided by delta x into 4 pi into m. Now let's put the values. Here the value of the Planck's constant, here the value of delta x 1 into 10 to the power 10, here is 4 pi, and here is the value of an electron, which is 9 into 10 to the minus 31 meter per second. And that, this is kilogram, and the overall value is obtained in the unit meter per second. And by calculating this ratio, we obtain 5.8 into 10 to the power minus 15 meter per second. So here is the correct option is D, 10 to the power minus 15, and the unit is meter per second. Move on to the next question. A solution of a free particle Schrödinger equation is this, and its solution is psi x equals to e to the power I kx, and which is again equal to cos kx plus I sin kx. So we have to derive the expression for energy E and momentum P of the particle. So here is the expression of psi x. So psi as a function of x, which is exponential I kx. I is the complex number. So d psi by dx, that means d psi x by dx equals to what? This is I k into exponential I kx, because differentiation of e to the power something is again e to the power something, then that something value is differentiated again. So differentiation of I kx with respect to x is I k. So it is I k into the exponential value again repeated. And the double differentiation is again I k is repeated here. So I k into I k is minus 1 into k, that means minus 1 into k into k, that means minus k squared. And here exponential value is repeated again. And this is nothing but psi x. So we have replaced this by psi x. So finally we have got minus k square into psi x. We have another solution of this equation is psi x equal to cos kx plus I sin kx. So the first differentiation is this one, and the second differentiation is this one, and this is nothing but minus k square into psi x. Therefore d2 psi x by dx square, in both cases from the both solutions we have got the expression minus k square into psi x. Now the equation which is given is minus h square by 8 pi square m into d2 psi x by dx square equals to e psi x. Or if we rearrange this, then we get this expression d2 psi x by dx square equal to minus e. This 8 pi square m goes to the numerator in the right hand side, and h squared goes to the denominator in the right hand side, and psi x as usual. Now comparing this equation with the derived equation, we get what equation we have derived, that this value d2 psi x by dx square is nothing but k square minus k square into psi. Okay, so if we compare them and remove this psi x, then k square psi x become k square, and minus e to the power 8 pi square m by h square psi x becomes minus e into 8 pi square m by h square. So these values are actually equal, and this way we can get the final energy expression. And this energy expression, by just rearranging this, we get the expression h square k square by 8 pi square m. So this way we have to calculate the energy of the particle. Now for a free particle, for a free particles, here is actually grammatical mistake. It should be free particle. Okay, potential energy V equals to 0. Yeah, definitely potential energy, there should be zero potential energy for a free moving particle. Therefore total energy E equals to kinetic energy plus potential energy equals to T plus V equals to T plus 0, that is equals to T, where T is the kinetic energy. Therefore this expression h square k square by 8 pi square m equals to half mv square, because kinetic energy is nothing but h square k square by 8 pi square m here. So here this is the energy. Okay, this is the total energy. So total energy has the expression this one, and this is nothing but equal to the kinetic energy. So the expression of kinetic energy is nothing but equal to this expression of total energy. So these two are equal here, and from which we can find the value of mv whole square. Just take this m to the right hand side, so you get the mv whole square, and take this 2 to the left hand side, so you will get the expression of mv whole square. And mv whole square means p square, and if you solve this, p square equal to h square k square by 4 pi square, then you will get the value p equals to hk by twice pi. So this way you can find out the value of energy and momentum. So this way you have to solve this question. So that's all for today. Thank you. Have a nice day.